reactions during the order. This is the final part of our two-part series this afternoon. My name is Patrick Mills from Texas A&M University. My co-chair is Thomas Degnan from ExxonMobil Research. Our first speaker today, did you see the title there? Effect of sulfur on properties of molybdenum carbide and platinum molybdenum carbide catalyst. It's from the workers from the University of Michigan, and the paper will be presented by Josh Schaide.
All right, thank you very much. Good afternoon, everyone. I'd like to take this opportunity on behalf of my co-authors to present our work on the effect of sulfur on moly carbide and platinum supported on moly carbide catalyst. Just a brief introduction. We all know that poisons are a major issue in catalysis, specifically sulfur, due to its very severe and sometimes irreversible deactivation, even at very low concentrations. The plot here shows that for a number of different metals, we see more than 99% loss of activity with just 15 parts per billion of sulfur. Sulfur is also prevalent in virtually all fossil fuels, and so a specific area where this is really important is for hydrogen production. So we're looking for sulfur-tolerant catalysts specifically for hydrogen production. And the reason this is kind of a big issue is there's a growing demand for hydrogen, specifically for the production of proton exchange membrane fuel cells, for ammonia synthesis, for alcohol synthesis. And currently more than 90% of our hydrogen is produced by the reforming of fossil fuels, which I mentioned are laden with sulfur. So one class of materials that present themselves as potentially being resistant to sulfur poisoning are early transition metal carbides and nitrides. These materials are just carbon or nitrogen incorporated into the parent metal lattice in the interstitial sites. Shown here is a beta moly carbide example with the molybdenum atoms in blue and the carbon atoms shown in green. And these materials have been shown to be active for a variety of reactions: hydrogenation, isomerization, water gas shift. The list goes on. And as I mentioned, they've been reported to be resistant to sulfur poisoning. I've shown here just a few examples from literature of different reactions over moly carbide in the presence of different sulfur compounds. And what I want to kind of focus in on is that most of these reports of sulfur tolerance have been at very high temperatures. And so it really hasn't been explored how these materials work under lower temperature in the range of 200 to 250 degrees C conditions and atmospheric pressure. Now in our group, we've done some work on these materials, moly carbide and platinum supported on moly carbide, for both the water gas shift and the methanol steam reforming reactions. And shown here are just the activities for the hydrogen production rates for these two materials for moly carbide for steam reforming and for shift compared to the commercial catalyst copper, zinc, aluminum. And when we support platinum onto these materials, we get a marked shift upward in the activity, much higher than both the moly carbide support and also the commercial copper, zinc, aluminum catalyst. So our goal here is to use the water gas shift and the methanol steam reforming reaction as test reactions to study how sulfur affects the hydrogen production activity of these two materials in moderate temperature regimes of about 200 to 250 degrees C and atmospheric pressure. And then also look at how sulfur affects the bulk and the surface structure of these materials and try to link up that change in structure with the change in catalytic activity. Now I want to go ahead and talk first just about how we synthesize and characterize these materials. These are synthesized using a temperature program reaction with 15% methane hydrogen of a molybdenum trioxide. And we produce the moly carbide, which is pyrophoric, so we have to passivate it, so we create an oxide layer on the surface. When we create the platinum supported on moly carbide catalyst, prior to passivation, we actually take the material and do a wet impregnation with a platinum salt. We further reduce it in hydrogen and then passivate again, giving us our, in this case, a 4% nominal weight loading of platinum on moly carbide. The XRD patterns you can see are very similar for moly carbide and platinum moly carbide. They match up with the reference peaks for moly carbide shown here. However, we don't really see any strong peaks for platinum, which just means that these platinum particles or domains are likely below the resolution of our X-ray diffractometer. So we explored this a little bit further using scanning electron microscopy. And what you see is on the left is moly carbide, on the right is platinum moly carbide. These are the same magnification, and there's quite a bit difference in the surface morphology. And when you zoom in, quite a bit closer, you can now see that there appears to be some sort of particles, what we assume to be the platinum domains on the surface, in the range of particles of about 60 to 80, 100 nanometers. And we further characterize this to make sure that these are platinum using XEDS, and the dashed line locations there correspond to platinum peak positions. And you can see the platinum molycarbide spectrum has very strong peaks at those locations. So we know that more than likely those structures are the platinum on the surface. And this was further confirmed that our weight loading, our nominal weight loading, was met using ICP with about 3.7 weight percent. Now, before we run these catalysts for the reaction, since we have to passivate the surface, we have to remove that passivation layer to further activate the catalyst. So we pre-treat these catalysts in 15% methane hydrogen at 590 degrees C. And XPS spectra for Moly 3D and carbon 1s, what you see is that the surface is reduced. So in the case of, say, here we have the moly trioxide corresponding to these orange peaks. These are completely removed once the catalyst has been pre-treated. And the peaks corresponding to molycarbide here are increased drastically. So we're basically removing oxygen and recarburizing our surface. So now that we've characterized, we've pre-treated, we understand what our sample looks like under a variety of different techniques, we can go into our actual results regarding the sulfur tolerance. So this is molycarbide. So I'm going to focus just for most of this talk on molycarbide. I'll touch on platinum molycarbide at the end. So we have water gas shift and steam reforming shown here. And what you see is when we, sorry about that. When you turn on 5 ppm of H2S, you get about a 90% decrease in activity for water gas shift, but only about a 40% decrease in activity for steam reforming. When you turn off the sulfur, there's no recovery of activity. However, when we regenerate, which again is the 15% methane hydrogen at 590 degrees C, we see that the steam reforming over molycarbide completely regains all of its lost activity. However, for water gas shift, we only regain about, say, 40% of our activity. So there's a clear difference of what's going on over the same catalyst, same temperature, same sulfur concentration, but a different reaction. And so there's some extra sulfur tolerance that's exhibited under steam reforming conditions than shift. And I'll mention this a little bit more later and discuss this. But first I want to talk about the effect on the structure. So first we wanted to look at the bulk structure. Are there any changes? So we exposed molycarbide to different concentrations of sulfur with imbalanced helium in the TGA. And then for 15 hours on stream, and then we performed X-ray diffraction. And what you see here is that there are no peaks shown at about 15 degrees that correspond to any bulk sulfide formation. So even up to about 1,000 ppm at 240 degrees C, we don't see any change in the bulk structure. So these materials are relatively resistant to bulk sulfidation. We also looked at SEM again of the spent materials and saw no change in surface morphology, no change in the platinum particles. And we further investigated looking at the surface area, so BET surface area measurements of the fresh catalyst, the spent catalyst just exposed to pure feed, and then the spent catalyst exposed to the pure feed plus the sulfur. And all catalysts have the same surface area within error. So nothing here really indicates why we are getting this change in our catalyst activity. So we turn to XPS to look at what's going on the surface. Now what we see here is that the sulfur 2P spectrum for molycarbide under water gas shift conditions has a very strong signal. However, for methanol steam reforming, we don't see any peaks for sulfur in the sulfur 2P XPS spectra, both when the catalyst has not been regenerated as well as when the catalyst has been regenerated. And this fits pretty well with what we've seen in the activity where there's greater sulfur tolerance for steam reforming than for water gas shift. And the peaks here, typically noted in literature, correspond to sulfur directly adsorbed on molybdenum, a sulfur 2- phase in blue, which is molysulfide, and also the evidence of elemental sulfur. Now to go ahead and discuss what I mentioned earlier about this higher sulfur tolerance under steam reforming conditions than water gas shift conditions, one possible explanation for this is that surface oxygen plays a role in how extensively these materials are sulfided. And this was proposed by Wei in 1998. They exposed molynitride to H2S and hydrogen at 400 degrees C. And what they saw was that the sulfur 2p signal from these sulfided materials was much higher when the material was passivated, so has oxygen on the surface, versus when the material is not passivated, so presumably very little oxygen on the surface. And this is further shown by their XPS sulfur to molybdenum ratios. So there's a much higher sulfur to molybdenum ratio on the passivated material than on the pre-treated or non-passivated material. So oxygen seems to play a role in how extensively these materials are sulfided. To investigate this for our materials, we performed in situ XPS. So we took molycarbide, we passivated it, we took our sample passivated, took a sample pre-treated, and then exposed it to both water gas shift conditions or methanol steam reforming conditions. And the one thing you want to notice is that to make all these show up, the oxygen signal here under steam reforming conditions had to be multiplied by about 8 times to be on the same scale as the oxygen 1s signal for the water gas shift catalyst. And what we see is that, so the passivated, what I showed you before, passivated 2.5, as you pre-treat, which I showed you, reduce the catalyst, so you decrease the oxygen to moly ratio. Now under water gas shift and steam reforming conditions, we have a much, much higher oxygen to moly ratio under water gas shift conditions than steam reforming conditions. So this seems to lend itself to this belief that the more oxygen that's on the surface, the greater sulfidation of the catalyst. So this is one possible explanation for why we see this marked difference in the sulfur tolerance of these materials. As I mentioned, I wanted to talk a little bit about platinum molycarbide. This is a similar plot to what I showed earlier, and it shows similar results. The water gas shift over platinum molycarbide decays faster than under steam reforming. But one key difference is that when we regenerate, we get absolutely no recovery of activity for water gas shift, and we only get about a 20% recovery for steam reforming. So there seems to be a greater or a stronger interaction of platinum with the sulfur, causing our catalyst to be more susceptible. And when we perform TGA over this, so we just expose molycarbide and platinum molycarbide to 5 ppm H2S, we see a much faster uptake of over platinum molycarbide of the sulfur than we do over molycarbide. So it seems to have a stronger interaction. And when we look at XPS, I showed this before for molycarbide. So this is steam reforming molycarbide. We didn't see any sulfur. Now, when it's platinum molycarbide, there's very strong sulfur signals, both without being regenerated as well as being regenerated. And you see specifically, again, sulfur adsorbed on molybdenum, the sulfur 2- species, which in this case could be either molysulfide or platinum sulfide. And you even actually end up with these sulfate species at higher binding energies. And this seems to make sense that these peaks could be platinum sulfide if you look at the thermodynamics. So at 240 degrees C, in the presence of H2S, it's thermodynamically downhill here to produce platinum sulfide. However, when we try to regenerate the catalyst at 590 degrees C to reduce that platinum sulfide back to platinum metal is actually thermodynamically uphill. So it makes sense that we would still see these very strong peaks on the surface. So with that, I'd just like to conclude saying that for the hydrogen production rates for both of these catalysts was definitely affected with only 5 ppm of H2S. We saw the formation of a number of different species, molysulfide, platinum sulfide, sulfur adsorbed on molybdenum. However, we noticed that molycarbide exhibited a much better sulfur tolerance under steam reforming conditions than it did under water gas shift conditions, and this seems to lend itself to this belief that the oxygen content on the surface affects how extensively these catalysts are sulfided. And last, as I showed, platinum molycarbide is affected more than molycarbide due to what appears to be a stronger interaction with sulfur than molybdenum carbide. And with that, just a few acknowledgments. The Rackham Travel Grant, the Electron Microbeam Analysis Lab, where I did a lot of the SEM and XPS work, the Michigan Memorial Phoenix Energy Institute, and the NAM COCUS Award. And with that, I'd like to thank you all and open the floor for any questions.
Okay, so we have plenty of time for questions. Yep. Yes, could you please go to the microphone and identify yourself?
Rob Savinelli, UCSB. Can you explain about the in situ XPS? I couldn't tell what was in situ?
So we pretty much have a reaction chamber attached to the XPS instrument, and so under vacuum we transfer them in. We can pre-treat, 15% methane hydrogen, and then we pull vacuum, transfer it back in to run basically XPS, and then again transfer it back out, expose it to the water gas shift conditions, again pull vacuum and bring it back in. And so it's never exposing it to air, pretty much keeping it under vacuum in between the exposure to the different conditions. Yep.
Yes, there's another question, yes.
I'm Lina Ferdous from Rentaking Corporation. My question, how did you do XRD on molybdenum carbide? Because like when you did the reaction, you passivated it.
Mhm.
So have you done XRD on passivated sample? Or?
Right. Everything that XRD was performed on is passivated. Correct. Yes.
Okay. Thank you.
Yep.
Yes, another, yes.
Imita Özkan from Ohio State. When you were looking at the effect of sulfur on the activity, there was a gradual decline of activity even before you introduced sulfur.
Right.
What is the mechanism for that decline? And if you kept it online longer, do you think it will just keep on going down, or is there a steady state performance level when it reaches that was?
Right. So this is without sulfur, just 20 hours on stream without any sulfur or anything, just leaving it in there at 240 degrees C. And you can see it begins to steady out pretty well. But you do, as you mentioned, get this pretty standard stabilization period, as we call it. And we're not quite sure what that is. It could potentially be some oxygen formation on the surface because molybdenum loves to be oxidized. And so you may have some initial CO dissociation or something possibly over the surface that causes oxygen to be deposited. That causes that gradual kind of stabilization and structuring of the surface. Yeah.
Thank you.
Okay, we have time for some more questions. Okay, if not, let's thank our speakers.